All right, in this video, we're going to go through our AP style rating for our interpreting graphs. So when we are increasing, we know that our derivative, f prime of x, is greater than 0. When we are decreasing, f prime of x is less than 0. When we have a relative maximum, f prime of x is going to change. So f prime of x changes from positive to negative. And when we have a relative minimum, f prime changes again, but the minimum is going to be changes from negative to positive. Now, when it's concave down, that's going to be looking at our second derivative. So concave down when our second derivative of x is less than 0. Concave up when our second derivative of x is greater than 0. And have a point of inflection when our second derivative of x changes signs. It must change. If it is just equal to 0, that is not enough. It has to look at those pieces and change signs. Now, for number 2, we're going to actually answer with the numbers here. Answer the following questions with letters instead of numbers. There are no letters on there, so I forgot to change the directions. Let's go intervals of increasing and decreasing. Now, this is our F graph, so it's exactly as we see it. We're going to be increasing from -2 to 1. And decreasing from -infinity to -2. And then again from 1 to positive infinity. We are concave up, so that curve that's facing up. Let's go all the way to 0, 0, so we keep even numbers. It's hard to tell on the f of x graph where actually it's switching in particular. Somewhere along here it's switching for that point of inflection. To keep everything nice, I'm just going to go concave up from -infinity to 0 and concave down from 0 to positive infinity. Now, since that switching happens at 0, or we're going to call it 0, that would be my point of inflection. So point of inflection would be at 0, 0. My relative minimum would be down here. Oh, I don't have a y value. So at x is equal to -2, and a relative maximum here at x is equal to 1. Now, would you be able to give full ordered pairs for part B? Why or why not? We would. Yes, we would. Because if we had a y-axis here, we'd be able to end up giving out what those ordered pairs would end up being. Or we have the f of x graph because we have the original function. All right, now let's go to f prime of x. Let's look there. So now this is the derivative graph. So where our derivative is positive, that's where the graph is increasing. So where is it? Above the x-axis. All right, and this is where it's going to be a little bit harder to answer with the numbers, but we're going to do our best. So above the x-axis is where it's going to be increasing. So that's going to be -infinity, and I would say -3.5. And from 0 to, let's go 1.9. It's pretty close to 2. Wherever it's decreasing is where it's below the x-axis. So that would be our -3.5 to 0. And let's make that more of a point, 3.5. And then from 1.9 to positive infinity. Right. So the first derivative graph, when you're looking at increasing and decreasing, we're looking at the signs of that first derivative to tell if it's increasing or decreasing. If we're going to look at our concave up and concave down, then we're going to be looking at the slopes. So now I'm going to look at the slopes here. And when the slopes are positive, that's when it's concave up. So this is going to be concave up from -2 to 1. And then it's going to be concave down whenever I have negative slopes. So that's going to end up being from negative infinity to -2 and from 1 to positive infinity. Then let's find our relative max. Our relative maximum then would be where we're switching from positive to negative. So I would have a relative max when my graph is going from positive to negative. Oops, let's get my marker back. That would be right here. And then also over here. So that would be at x values of, what do we say, -3.5 and 1.9. Then we'll have a relative min when it's going from negative to positive, and so that would be an x value of 0. And then the points of inflection are where our slopes are changing. So our slopes are changing from decreasing to increasing at -2, and then also again at 1. Now, are you able to give full ordered pairs for the parts in part D? And no, that's going to be not able to happen because we do not have an original function to plug anything back into. All right, next one. We're just looking at the graph, actually, exactly as we see it. This is g of x, not the derivative of anything. So we're just looking for how many points of inflection that this would have. So I'm just going to look at the concavity. This is concave up. Then this portion is concave down. And then I have a little bit that's concave up. And then a little bit that's concave down, tiny, tiny piece, and then it switches right again to back to being concave up. So if we're looking for how many points of inflection, we're looking at how many times it changes. So that would be 1 here, 2, 3, 4. So we would have 4 points of inflection. And how do you know is because it switches 1, 2, 3, 4, 5 times. So the points in between there would be 4 points in between there. Now the next one is how many horizontal tangents does this one have? So you're following along with your slopes of your tangent lines. And so I would have a horizontal tangent down here. That doesn't really look horizontal. All right, let's try that again. Here, horizontal tangent, that's 2. Horizontal tangent here, that's 3, 4, and 5. There are 5 horizontal tangent lines. And how do we know? Well, that's when the slope is going to end up being 0. And really that's our minimum and maximums because we have 5 extrema on this graph. None of them are like cusps, because if we would have a cusp, it would be undefined, not a horizontal tangent line. And so we're looking at those and we have 5 extrema on this graph. So that's what gives me the 5 horizontal tangent lines.